Okay, it is visible. Okay, so we have been discussing mechanical rotational system. The symbols that you must that are used in mechanical rotational system are the angular displacement, which is measured in radians. It is denoted by theta. Okay. Next is the angular velocity. Okay. So the angular velocity. Angular velocity is measured in radians per second. It is denoted by d theta by dt. Angular acceleration amount, which is measured in radians per second square. It is denoted by d square theta by dt square. Okay. So here capital D is the applied torque measured in Newton meter. J is the moment of inertia, which is measured in kN per meter square per radians. B is the rotational frictional coefficient measured in Newton meter per radians per second. Okay. Next, K is the stiffness of the spring. It is measured in Newton meter per radians. All these terms you might be already knowing. You might have already learned. Okay. So you might have already learned in your intermediate itself. Okay. So let's go for the next slide. Okay. So torque balance equations of the idealized elements similar to your mechanical translational system. Okay. In this case also we are going to discuss the torque balance equations of the idealized elements. So let us consider an ideal rotational mass element. Okay, so here, we are going to consider moment of inertia J. So we are going to consider moment of inertia J of the mass. So you have instead of in your mechanical translation system, we used to write the mass M. Here, in the case of rotational mechanical system, you will write J. Okay, so here rotational movement is there means torque is applied. Okay, so what is our input here? E is the input, torque is the input. So when a torque is applied, what will happen? There is an angular movement. There is an angular movement. So theta is our output. So input for the mechanical rotational system is what? T, torque, and angular displacement. Okay, angular displacement will be there. Okay, so angular displacement is represented by. Okay, so here we are considering an ideal mass element. Okay, so we are neglecting what? Friction and okay, here we are neglecting friction. So we are considering an ideal mass element. Ideal mass element. So we are neglecting what? Friction and elasticity. Okay, so rotational mechanical system can be represented by three elements: mass, moment of inertia of mass, okay, torsional friction and torsional velocity, you can say. Okay, so among these three elements, we are considering ideal rotational mass elements. So ideal mass element we are considering, therefore we are neglecting friction and elasticity. So negligible. So this rotating element has negligible friction and negligible elasticity. Okay, so similar to your mechanical translational system, in that case also mass was directly proportional to the acceleration. Similarly here also moment of inertia is proportional to the angular acceleration. Okay, so the opposing torque due to the moment of inertia. Okay, in the case of mechanical translation system, it was the force, opposing force. Okay, so the opposing force due to the mass of the system was proportional to the acceleration in the case of mechanical translational system. In the case of mechanical rotational system, the opposing torque due to moment of inertia will be proportional to the angular acceleration. Okay, same terms, but a bit variation is there. So what is applied here? T is the applied torque. Okay, so let us consider Tj is the opposing torque due to moment of inertia of the body. Okay, Tj is the opposing torque due to moment of inertia of the body. So Tj will be proportional to what? It will be proportional to the angular acceleration. So d square theta by dt square. So remove the proportionality, replace it by some constant j. Okay, remove the proportionality, replace it by some constant j. Okay, so according to Newton's second law, what is the applied torque here? Applied torque is capital T. Opposing torque is capital T suffix j. So applied torque will be according to Newton's second applied torque will be equal to the opposing torque. What is the opposing torque equation? J into d square theta by dt square. Okay, so this is our ideal rotational mass. Okay, let us consider one more ideal case. We are considering an ideal rotational frictional element here. Ideal rotational dashpot with one end fixed to the reference. So we are considering an ideal frictional element with one end connected to reference, another end is free to move. Okay, so whenever we say ideal frictional element means we will assume that the mass, moment of inertia, and moment of inertia and elasticity are negligible. And elasticity, okay, are negligible. So we are considering only the frictional element here, and that too we are assuming one end is connected to the reference. Okay, so since one end is connected to the reference, okay, so this is the applied torque. This is the angular displacement. So input is capital T. Input is capital T. Now is it okay, voice? Okay, so the input is capital T and output is the angular displacement. Okay, message me, is there any disturbance? If there is any disturbance, inform. Okay, are you able to hear me? Now, okay, okay. So here I will erase all the ink marks. So here we are applying input. Input is the applied torque. So when torque is applied, what happens? There is an angular displacement of theta. So it is an ideal case of dash torque, means ideal friction element with one end connected to a reference we are considering. So moment of inertia is negligible and elasticity are negligible. Okay, so let us consider T is the applied torque. Okay, so let us consider T is the applied torque. T suffix B is the opposing torque due to friction. Okay, TB is the opposing torque due to friction. So friction opposing torque will be proportional to the angular velocity. What is angular velocity? D by dt of theta, or d by d theta by dt is the angular velocity. If you remove the proportionality, you just replace it by some constant. So TB is d into d theta by dt. So what is according to Newton's second law? According to Newton's second law, 1 minute. Okay. 1 minute. Okay. So I saw this. Sorry. So according to Newton's second law, the applied torque will be equal to the applied torque will be equal to the opposing torque. So what is the applied torque here? T is the applied torque. TB is the opposing torque. So T is equal to TB, that is equal to B into d theta by d. Okay. So according to Newton's second. This is for ideal frictional element with one end connected to a reference. Okay. So let us consider an ideal frictional element with angular displacement at both ends. Okay, so there is angular displacement at both ends. Okay, for this frictional element. Frictional element means here I have written dash dot. Okay, so it has angular displacement at both ends. So what is the applied torque here? I am applying a torque of, I have written here in this figure I have written T1 and theta 1. Okay, where at T1, okay, 1 minute. So, I'm applying it of T. I don't want this T1, so I want to cut it. So I don't want this T1, so I want to perform some changes here. So I want to apply only T. I don't want T1. Okay. So I want to make this change. So applied torque is T. There is an angular displacement. Since both the ends are free to move, there is an angular displacement of theta 1 and theta 2. Okay, so there is an angular displacement of theta 1 and theta 2. Okay, so two angular, so differential velocity I must consider because it is a frictional element. Because it is a frictional element, I must consider the differential velocity. So let us consider so applied torque is T and opposing torque is TB. Okay, same terms here also we are considering. So TB is proportional to what? Differential velocity. Theta 1 by dt of theta 1 minus theta 2. D by dt of theta 1 minus. So there is a message. Okay, d by dt of theta 1 minus. Okay, sometimes I am leaving my mic. Okay, it won't happen. I want to use the system, that's why I just left the mic. I'll keep like this. So that I okay, now it's okay. Okay, so T is the applied torque. Let us consider the opposing torque is TB for the frictional element. So notations are always okay. You can consider any notation. So it is proportional to the differential velocity here because both the ends are free to move. So if you remove the proportionality, replace it by some constant b. Okay, so when I replace it by some constant b, so TB will be equal to b into d by dt of theta minus theta 2. Okay, so what is according to Newton's second law? According to Newton's second law, applied torque is equal to what? The opposing torque. So T equal to TB equal to b into d by dt of theta minus theta 2. Okay, so I hope you understood. It's very simple to understand. Okay, next term, let us consider one more ideal case. Ideal elastic element or a spring here. Okay, I'll consider an ideal elastic element means I'll consider only elasticity is there, but no, only elasticity is there, but no moment of inertia and friction. So another ideal case is only elasticity is there. Okay, so the opposing torque is only due to elasticity, not due to moment of inertia and friction. So when torque of T is applied, okay, and I am also considering one end of this elastic element or this spring is connected to a reference. Okay, one end is connected to a reference. Okay, so when torque is applied to this spring, there is an angular displacement of theta. Okay, when torque is applied, there is an angular displacement of theta. Okay, so the opposing torque. Let us give some notation T suffix K. Okay, opposing torque due to elasticity. The opposing torque due to elasticity. Let us consider it as some T suffix K. So applied torque is T, you know. Okay, so that will be the opposing torque will be proportional to directly proportional to the angular displacement. That is K. Okay, if you remove the proportionality, you replace it by some constant K. So according to Newton's law, applied torque is equal to the opposing torque. What is the opposing torque? Tk. So T equal to dk equal to K into theta. This is the equation when for an elastic element which is connected to the reference. Now let us consider an ideal spring with angular displacement at both ends. Okay, this is it. Okay, so there is an angular displacement at both ends. So what is the applied torque here? Applied torque is T. I am applying a torque of T. I am having angular displacement at both ends because they are free to move. Okay, so let us consider opposing torque due to elastic element is some Tk. So Tk will be directly proportional to the difference of these two, theta 1 minus theta 2. Okay, so the Tk will be directly proportional to the difference of the angular displacements, both the angular displacements. Okay, so if you remove the proportionality, that will be equal to K. Tk is equal to K into theta 1 minus theta 2. So according to Newton's second law, T is equal to Tk equal to K into theta 1 minus theta 2. Okay. So this is it. Okay, anybody up to here? If you have any doubts, you can ask. Anybody, you can unmute yourself and you can ask me anything which is not understood by you. Anything which is not understood by you, you can ask me. Otherwise, I will proceed. Okay. So let us solve some problems on this. Okay. So we have to write the differential equations governing. Okay, I have full.
Sorry, my microphone, sir, my speaker connection was loosely connected. I didn't pin it properly. I hope now it is clearer to you. I think now it is okay. I didn't pin it properly. Huh? My
Yes,
earphones
ma'am. Crystal clear.
connection. Now it is okay, isn't it? I didn't pin it properly. I thought I have pinned it properly, but it was loose connected. That's why I think you had disturbance till now. Okay, I didn't pin it properly. I didn't. Okay, that's all. I think from this moment onwards there will not be any disturbance because of your messages. I got a doubt. I just checked it. I didn't pin it properly. Okay. Now let us solve some problems. Okay. So write the differential equations governing the mechanical rotational system shown in the figure. Obtain the transfer function of the system. Okay, we have to determine the differential equations as well as we have to write down the transfer function. So always read the question properly whenever whatever question is given to you. You must read properly and you must know what they have asked you to find out. Okay, so you must write down the differential equations governing the mechanical rotational system as well as transfer function of the system. So this is the system that is given. So in this system we can see two moment of inertia elements J1 and J2. So this is the applied torque they have already clearly mentioned here. This is the output they have clearly mentioned. Okay, so I can see a spring element, I can see a frictional element. Okay, similar to your mechanical translational system, in this case also you must write down the free body diagrams. Okay, so first of all you must know what is the input. What is the input here? Input is the applied torque. Applied torque is the input. What is the output here? What is the output here? Output is the angular displacement. Okay, angular displacement is the output. Now I know my inputs and outputs. Okay, so what will be my transfer function if I want to determine the transfer function? My transfer function will be the Laplace transformation of theta. Means Laplace transformation of theta is theta of s by theta is the output. Therefore, theta of s by t of s will be my transfer function. Transfer function. my transfer function. This will be my transfer function. Okay, my transfer function is the output, Laplace transform of the output by Laplace transform of the input. Okay, so this will be my transfer function. So let us see the free body diagrams. Okay, so at node 1, so how many nodes are there? 2 nodes are there. J1 is one node, J2 is another node. So I will actually in this case we can consider some other figure, some other. Okay, I will show it later on. Okay, input amma, input applied is t, angular displacement is the output, Laplace transform of t is t of s, theta is theta of s, theta 1. There are two displacements. No, there is only one displacement. Two element. Okay, so since there are two nodes are there, we are considering two displacements. See, theta 1 is not mentioned here. Theta 1 is not mentioned here. So we will consider at node at node 2 this output theta is mentioned. At node 1 node no displacement, angular displacement is not mentioned. So you will assume the displacement at node 1 is theta 1. Okay, so theta is the displacement at node 2, angular displacement. At theta 1 you will assume, so theta 1 you will assume as the angular displacement at node 1. Okay, of course the transfer function that you require is theta of s by t of s. Okay, here the system has two nodes. Okay, so they are J1 and J2. J1, J2 are the two nodes here. Okay, so you have to determine the differential equations governing the system. Okay, so let us consider the first free body diagram at node 1. That is J. So angular displacement, we are assuming it is not mentioned in the question. Angular displacement is not mentioned in the question, so we will assume the angular displacement at node 1 as theta 1. Of course, the applied torque at node 1. Okay, at node 1, this is T is the applied torque. Okay, at node 1, T is the applied torque. T is the applied torque at node 1, and we will assume the angular displacement. It is not mentioned, but we will assume some angular displacement T1. Opposing torques, one is due to the, here how many elements are there? The moment of inertia and this elasticity, okay, of this. So only two opposing torques will be there. So opposing torques at node 1 will be Tj1 and T. Okay, and that's all. So there are only two opposing torques at node 1. Those are Tj1 and Tk. So two opposing torques are there at this node 1. Okay, so what is the applied torque? T. What are the opposing torques? Tj1 and Tk. So applied torques will be equal to the opposing torques. Okay, so applied torque is what? Applied torque is T. Opposing torques are Tj1 and Tk. So summation of these two opposing torques will be equal to the summation of the applied torque. So Tj1 is the moment of torque due to moment of inertia. Torque due to moment of inertia will be proportional to the angular acceleration. Okay, so it will be proportional to the angular acceleration. So what is the constant here? J1. Okay, and it is the spring, so it will be directly proportional to the angular displacement. So here K is free to move on both ends. K is free to move on both ends. Okay, so both ends are free. For K, both the ends are free. So we must consider the differential angular displacement. So the differential angular displacement is actually this K we are considering with respect to node 1. So at node 1, what is the displacement? It is theta 1. So theta 1 minus theta, angular displacement at node 2. Okay. So if you remove proportionality, replace it by some constant K. So Tk is equal to K into theta 1 minus theta. Okay. That's it. Okay, so you know these equations, you can easily write it down, substitute these values, and you will get a differential equation. So this is the differential equation which governs the behavior of the body, okay, rotational behavior of the body at node 1. Okay, so now take the Laplace transform of this. What do you get? You will get J1, okay, Laplace transform of this equation into s square of s square into theta of s plus k into theta 1 of s minus k into theta of s equal to t of s. Okay, it is equal to t of s. So that is it. J1 into s square theta 1 of s plus k into theta 1 of s minus k into theta s equal to t of s. Okay, just to simplify this, take theta 1 of s common and theta of s common. Okay, you will get this equation number 2. Okay, now consider node 2. So at node 2, applied torque is 0. Okay, no torque is applied. At node 2, T is 0, applied torque is 0. Okay, angular displacement is already mentioned at node 2, that is theta. What are all the opposing torques? Let us see. At node 2. Okay, so let us see the opposing torques at node 2. Okay, opposing torques are, wait, opposing torques are torque due to moment of inertia. Okay, and another opposing torque is due to the elasticity. Another opposing torque is due to the frictional element connected to it. So this at node 2, at J2, okay, at J2, okay, these are all the opposing torques. What is the applied torque at J2? Applied torque is equal to 0. What is the angular displacement is theta. Whereas this, in this case, applied torque is T, angular displacement is not mentioned, so I am assuming theta 1 in this case. Okay, so in this case, applied torque is 0. Applied torque is already, angular displacement is already mentioned, so you will consider it as theta. Okay, some terms, if they are not mentioned in the question, you have to assume. Okay, so 3 terms, Tj2, Tb, Tk. What is J? Moment of inertia, torque due to moment of inertia. So it is equal to J2 into d square theta by dt square. Tb is torque due to friction, so B into d theta by dt. Tk is torque due to elasticity, K into differential displacement. Here in this case, it is theta minus theta 1. Why? Because you are considering node 2 with respect to node 2. Okay, so according to Newton's second law, opposing torques will be equal to the applied torque. Applied torque is 0 here. So opposing, these are the opposing torque. Okay, so you just substitute the equations. Okay, and simplify further, you will get this differential equation. So this is the differential equation which governs the behavior of the body at node 2. Okay, now take the Laplace transform. It is J2 constant, therefore write down constant. This is the d square theta by dt square. So s square into theta of s. This is B, And d theta by dt is s into theta of s into theta of s, k, write it down as it is, theta of s, k, theta 1 of s. Okay, so you just in this take common theta s and theta 1 of s, you will get one equation. Okay, and in this equation determine theta 1 of s. So determine theta 1. Substitute this theta 1 of s in equation number 2. Okay, so where is equation number 2? This is our equation number 2. Time అయిపోయిందమ్మా. Okay. Okay, so okay, I will continue in the next class. Okay, so you have another class also. Okay, so I will continue in the next class. I will take the attendance. If anybody has doubts, you can ask me. I will take the snapshot. I have to take the snapshot. Okay. I'll take the snapshot, Amma. Okay, I'm taking the snapshot.